So we talked about elasticity. We went over problems with elasticity. Now we're going to relate it back to the demand curve and how elasticity relates to the demand curve and how elasticity relates to total revenue. So anytime we're talking about a demand curve, it helps us to go ahead and draw one, right? So we put price on the y-axis, quantity on the x-axis, right? We use our mnemonic about the alphabet, LMNOP, P comes before Q, P is to the left of Q, okay? Then we're going to have a demand curve, which we know is downward sloping, right? Downward sloping demand, they both start with the same letter D, so that's the way that we can remember that if we're having trouble remembering it. And we find that we get a demand curve here that starts at $40. We're given a point here, 30 and 20. And we're given a point here, 20 and 40. So right now, before we do anything else, I would like you to calculate the own price elasticity of demand between these 2 points on the demand curve. So what is our formula for elasticity? Elasticity of the quantity of X and the price of X is equal to what? The percentage change in the quantity of X divided by the percentage change in the price of X. So this is going to be my Q2. This is my Q1. This is my P1. And this is my P2. And so this ends up being, so my percentage change in my quantity, right, ends up being 40 minus 20 divided by 40 plus 20 over 2. Everybody clear with how we got that? Old minus new.
I have a question.
Yes.
So like for P1 and P2, if you go downward, let's say like you said 20 for P1, 30 for P2.
If I did that, then I would have to switch the Q1 and Q2. So if I said that 20 was P1, I would have to make sure that 40 would then be Q1.
Does make sense.
It's because it's a coordinate pair that we have here, right? So this is 40, 20. It really doesn't matter. You bring a very good point up that it does not matter which one is P1 and which one is P2. All that matters is that we keep them together. They're pairs. They can't be separated. Yeah, good question. So that's going to be our percentage change on the top. And then our percentage change on the bottom is the difference in the prices, right? And so again, we have to, if we want Q2 minus Q1, we got to go P2 minus P1. So we end up with 20 minus 30 divided by 20 plus 30 over 2. And so this ends up giving us what? 20 over 30 on the numerator and negative 10 over 25 on the denominator. And we can just plug this into our calculators, right? The other way that we could do this, since this is two fractions being divided by each other, the way that we unpack this algebraically is we take the first fraction and we multiply it by the inverse. So we're going to flip these guys. That is exactly equivalent to what this states over here. This is equivalent to this. And then from here, we can, cross out the 10. This just becomes 2. 2 times 25 is 50 divided by negative 30. We can get rid of the zeros. We end up with negative 5/3. We take the absolute value of it, because we know law of demand, right? It's an inverse relationship. As the price decreases, the quantity is always going to increase. So the absolute value of this, we say the elasticity of the own good is equal to just 5/3. And so what is 5/3? Is that less than or greater than or equal to 1?
Less than 1.
Nope.
Oh, it's greater than 1.
Greater than 1, right? Yep. It's a, what do they call it? Improper fraction or something like that, right? So it's really 1 2/3. We could also talk about it like that, right? 1 2/3. And so it is absolutely greater than 1, which means that this is elastic. And that's telling me the elasticity of exactly this point, right? The midpoint in between those 2 points. Does that make sense? What if I wanted to know the elasticity when the price is 30? So I don't want to know the elasticity when the price is halfway between 30 and 25, which is what I'm getting here when I'm using the midpoint formula, right? So I need more information to do that, right? So in order to do that, I would need an equation for this demand curve. And we're given an equation for this demand curve. We're given the linear, stupid glasses, they always fog up, inverse demand, which is P is equal to 40 minus 0.5 Q. Now on your own, I'm going to walk around to make sure that we can do this, because this was part of our homework the last week. Go ahead and find my regular demand curve. So this is my inverse demand curve. What is my regular demand curve?
I have a question.
Yes.
So you said the one we calculated 1, 2 by 3, that's the midpoint between 20 and 30 on the demand curve.
Yes.
How does the question ask to find us the midpoint between, or the on price elasticity does calculate the midpoint?
I'm teaching you 2 different ways to do it. So there's one way to do it when you just have 2 coordinate pairs, right? Which is to use that midpoint formula.
Okay.
But there's another way that we can do it when we have the demand curve,
Yeah.
and that's by using the slope and multiplying it by the quotient of the price and the quantity. So we're gonna exploit the fact that there's this formula. The elasticity is equal to whatever the slope is of the demand curve times the price over the quantity. And this M is, just whatever is attached to the P. So whatever is that P term when we finally end up with a equation, right? So it's, 100, and then this would be, plus 7, right? That would make this plus 7.
Okay. So your question was?
What's the regular demand curve? It's 0.5 Q. I apologize. It's 0.5. Yeah. I should have said 0.5. But yeah. So why do you don't put the 40? We need to isolate Q. So we don't put 40 in for Q yet. We're going to solve for Q to get the demand curve. So it's just an algebra problem where we're just solving for x. If this was just y equals 40 minus 0.5x, solve for x.
Oh. So do you want us to calculate the demand and when the price is $30?
No, I want the demand, just the general demand formula, and then we're going to calculate the elasticity when the price is $30. Close, but not quite. So if it's minus 0.5 Q, put 40 on the other side. So try it once again, just from scratch.
Okay.
I think your old work is messing you up. So how do you isolate Q and just get Q by itself? So there's no calculator that comes into it right now. So we can't do that actually. Well, what we can do is we can add plus 5Q to both sides.
Dr. McCarthy, so because it's like 0.5, can I do like 1/2 P?
Yeah.
Okay.
But why do you get 0.5 at the end?
Right?
So what is 1 divided by 0.5? If I have $50, how many half dollars do I get in a dollar?
2.
Oh, so sorry.
It's all good. It happens. Sometimes our brains just, it's okay. It's all good. It's happened to me a lot of times too. All right. So how do we solve this, right? So this is very important that we're able to solve equations like this, okay? So part of why I assigned the math review with the 73 concepts and everything, right, was to give you guys practice with this. I think that we need more practice, though. So what if this was just y equals 40 minus 0.5x? Would that be less scary if we're trying to solve for x? How do we solve for x? Well, we're going to take since we have a negative 0.5x, right, the first thing I'm going to do is I'm going to add 0.5x to both sides. So this negative 0.5x plus a positive 0.5x ends up canceling each other out. We then end up with y plus 0.5x is equal to 40. I'm trying to isolate x, right? So I need x to be the only term on the left-hand side of the equation. That means that I have to subtract y from both sides. So I subtract y from both sides. That takes that y away, right? Y minus y equals 0. And so we end up with 0.5x is equal to 40 minus y. Now that we have x alone, since it's not plus or minus anything, right? It's not a compound term. It's just all by itself. We can divide it by 0.5, and then we have to divide everything over here by 0.5, as if this is in parentheses. If we only divide one thing by 0.5, or if we only divide 40 by 0.5, or negative y by 0.5, that's an algebra mistake that we're making. So when we divide two items, whenever we divide a plus b over c, we can do this cool little thing where we can separate it into a over c plus b over c, right? So that equals a over c plus b over c. Just that's definitional. By definition, one of the properties of algebra. So in a similar way, we're going to take 40 divided by 0.5, and we're going to take negative y and divide it by 0.5. This 0.5 and 0.5 is going to cancel out. It's going to annihilate itself. We end up with x equals 40 divided by 0.5 minus 1 divided by 0.5 times y. Now, anytime that you're dividing by a fraction like this, you can also think about it as multiplying by the inverse of the fraction. So dividing by 0.5 is the same as multiplying by 2. You could also think of it as how many, I was asking Saranga, how many 50-cent pieces would you get if you cashed in $40, right? You would get 80. So 0.5 goes into 40 80 times. And a similar thing, if you had two 50-cent pieces, or if you had $1, how many 50-cent pieces would you get? You would get 2. So we can't forget that negative sign, and we end up with 2. So x equals 80 minus 2y. And then from this, we just substitute back into p equals 80 minus 2q. So maybe that's going to help with some of the math anxiety that I see you guys experiencing, to switch it to y and x, since that's a more familiar way that you're used to solving it. But it's very, very important that we're able to solve, manipulate these equations with two unknowns, right? With two algebraic terms. It's a big part of economics. It's a big part of finance. So now that we've found this demand curve, now we want to use that handy dandy elasticity shortcut, which says take the m, take that negative 2, plug it in there, multiply it by the quotient of the price and the quantity, and that gives me my instantaneous elasticity. So this is my elasticity at $30. So it's not the elasticity between $20 and $30, right, which is what the midpoint formula gives me. This is my elasticity at $30. P equals 30, Q equals 20. And so again, we take the absolute value of negative 3. In order to get positive 3, we find that's greater than 1, so it is elastic. And what do we find? We find that, that this point has a greater elasticity, right? The elasticity here is 3 compared to the elasticity here is 2.5. Oh, wait, no, 1.6. Thank you. 1.6 repeating. And so it would also make sense that if we calculated this elasticity, right, it's going to be less than 1.6. And so the point of this is to tell you that despite our first impression with elasticities and how they're related to demand curves, right? When we're first taught about elasticities and demand curves and stuff, let's just take a quick tangent. You know, we're told this is an elastic demand curve. That as the price decreases, the quantity does not increase that much, right? And then vice versa. As the price increases, the quantity doesn't decrease that much. So we know that inelastic curves are steeper, right? And then we have elastic curves, which are something like this, right? Where a shift in the price causes a very large change in my quantity. But what I'm trying to show you with this example above is that the elasticity is not constant on the curves. So at different points along the curve, the elasticity is changing, and specifically, it's getting more inelastic as you go towards the bottom and it's more elastic as you go towards the top. So again, the way to prove that, right, we'll go ahead and we'll calculate the elasticity at this point, 2040. So again, we're just going to use that m, that -2, and then we're going to multiply, because that's not changing, right? It's a linear demand curve, so the slope's going to be the same no matter what. And then I'm going to multiply this by my new quotient of price over quantity, which is 20 over 40. And so we end up with an elasticity of -1, or just an elasticity of 1. And so we find that as we go further and further down the demand curve, it's becoming more and more inelastic. Now, why do we care about this? Well, at the end of the day, total revenue is linked to the elasticity of the demand curve. What do I mean by this? So let's go ahead and let's get a new page. Let's get some graph lines here. Too big. It's better. No, smaller. Okay. And so we're going to have price over here, quantity here. We're going to have the same demand curve with 40 at the top. It's going to have a slope of 1/2. So it ends up at 80. That point that we just calculated was 20, 40. And we know that elasticity is 1 here. We know that the elasticity is greater than 1 here. And we know that the elasticity is going to be less than 1 down here. Right? Everybody following me? Cool. So, and this is our demand curve. So this relates to our total revenue in this really neat way. So when we look at total revenue is a concave function starting at 0 and maximum of 800. So this is our total revenue curve. So what is this saying? This is saying that when we're in the inelastic range, or sorry, when we're in the elastic range, total revenue can be increased by increasing price. It also means that when in the inelastic range, total revenue increases when price decreases. Oh wait, this is backwards. Decreasing price. And this is increasing price. Right? So let's see if we're in the if we're in the elastic range, by decreasing our price from, whatever this is, 35 or something. At 35, we're only making $600. Well, at 30, we're making $750. So at 20, which is the 30, not 35. And yeah, that's over here instead of there. So we're only making $600 when the price is 30, and we're selling 20. So since we're in that elastic range, we're going to want to go ahead and lower that price until we get to that point of unit elasticity, because the point of unit elasticity is the local maxima for the total revenue curve. So this is always the way that demand curves relate to their elasticity. At the higher ranges, it's more elastic, so lowering the price increases your total revenue. At the lower prices, it's inelastic, increasing the price is going to increase our total revenue.
I have a question.
Yes.
So is that the demand or the price?
What's up?
For the second graph,
Yeah.
the one that's horizontal, is that the price curve? That is the price?
What are you talking about? The price is the price is on the demand curve. It's right. It's this axis. So the price is changing every time, right? So we're saying if you're pricing your product at $30, right? And at $30, there's 20 units that are desired by the market, right? At $30, you're making $600, right? Which makes sense. 30 times 20 is 600, right? So what we're saying is that since we're on the elastic part of the demand curve, that decreasing the price is going to increase total revenue, right? So if we decrease the price from 30 to, let's say, 25, just for the sake of an example, right? At 25, that's when we're going to be selling 30 units. And that's when we're going to be making $750. And so we're going to make more money by lowering the price to 25 from 30, right? Because 25 times the increase in demand, 30, is going to equal 750, which is greater than 600. And so what it ends up being is that where that unit elasticity is the maximum point of the total revenue curve. So you want to be producing at that unit elasticity point because that's maximizing your revenue. So a lot of, it's like you're trying to price it in such a way that you're as close to that unit elasticity point of your demand curve as possible. And there may not be one, right? If it's like something like insulin or something like statins, like heart blockers and stuff like that, they have an elasticity of like 0.2, right? Because like if you don't take them, you're gonna have a heart attack and die. So of course, it doesn't matter what happens to the price, you're gonna take them. So there might not be a feasible range where there's unit elasticity. So the curves can be extreme enough that it's just inelastic the whole entire time, or it's just elastic the whole entire time. But when it's something that's more normal, with a slope of -1 or a slope of -0.5, which is what we have here, we end up having a change in the elasticity as we go along the curve. It's a weird thing to understand at first. It's very weird. So doing problems and stuff will help. The main thing to remember is these kind of rules over here, right? When it's elastic, you want to decrease price to increase total revenue. When it's inelastic, you want to increase price to increase total revenue. And when it's perfectly unit elastic, that's when the total revenue is maximized. So we have some extreme cases that we want to talk about as well when we're talking about elasticity.
Is it recorded, right?
Huh?
Is it recorded? Is it recorded?
Yeah.
Yes, it's recorded. In the top right, you can see it's recording up here.
Oh.
Yeah. And so we end up with, so what is this? What kind of demand curve is this? Let's think about it. What's happening when price increases? What happens to demand?
This remain the same.
Stays the same, right? So this is an elasticity of 0. And we would call this perfectly inelastic. So why is it 0? Well, the percentage change in the quantity demanded, the thing that's on the numerator, is going to be 0 no matter what, right? So anything divided by 0 is 0. Another math law. The laws of mathematics. Supreme cosmic powers. Oh, I have some backwards. I feel like a dummy. What's this demand curve? Talk me through what's happening here.
Demand is same. Demand remains same even the quantity increases.
Pardon?
I mean, if the change in quantity has no effect on demand,
The price stays the same.
price stays the same.
The price, it's not that the price stays the same. It's the fact that, so this is a little bit of, this is a strange one. It's the fact that if the price is changed at all, demand goes to 0. So like if they increase the price, demand just goes to 0. So it's the fact, so this is a perfectly elastic. So this is the extreme case where they're super responsive to price. If the price changes even by a little bit, they're going to go buy something else, right? So this is the case for something like wheat, right? Wheat is, that's highly substitutable. It's a very uniform good. You don't care where your wheat comes from, right? So if there's some wheat that ends up, being more expensive, you're going to stop buying that wheat and go buy a different variety of wheat or whatever the case may be, right? So this is a perfectly elastic demand curve where they're extremely sensitive to price changes. And so the elasticity for this one is represented by infinity, negative infinity. Why is it infinity? Well, because the formula for elasticity, percentage change in the quantity demanded over percentage change in the price, right? The percentage change in the price here is 0. So any number divided by 0 by mathematical law is equal to infinity. So this is essentially saying that all of the demand is going to change when you change the price.
So the first graph does not have many substitutes? Is that what you're saying?
Yes, the first graph has like 0 substitutes. Very good. And this is, you know, 1,000,000 substitutes. Yeah, very good question. So that actually dovetails really nicely into our next bit of notes. What are the factors that are actually impacting own price elasticity? So there are 3 main factors. We just talked about the first one, which is the availability and number of substitutes. The more substitutes, the more elastic. The more sensitive people are to the price changes, price variations. The second one is the time or the duration of the purchasing horizon. So when we talked about the elasticity from that harvard.edu PDF, you know, it talked about the short-term elasticity of gasoline is 0.8 or 0.2 or something, and the long-term elasticity is 0.8, right? So in the long run, when there's increases in the change of the price of gasoline, people start to buy more gas-efficient cars, or buy more hybrid vehicles or electric vehicles or things like that. Now, you can't make that adjustment right away, which is why our short-term elasticity of gasoline is so small. But when we are allowed some more time, when there's an increase in the time or the duration of the purchasing horizon, right, so that window leading up to purchasing, then that's going to be more elastic. We're going to be more sensitive to price changes. And the last one is the expenditure share of consumers' budgets. You know, how much is the price of a box of salt, right? It's like $1. It's like $1.10 or something, $1.50, right? If the price of salt were to increase by 75 cents and there was $2.25 tomorrow, would you still buy the salt? Yeah, you'd still buy the salt, right? But what if your rent increased by 50% and instead of paying $600 a month, now you're paying $900 a month? That'd be a different story, right? So the things that have a smaller chunk of your budget, you're less sensitive to price changes about. So rent, your car payment, you know, mortgage, all that kind of stuff, right? These large things, childcare expenses, right? You're more sensitive to changes in the price of those than you are to, say, the price of bread or milk or something that's a very small portion of our income. Now, when we talk about food as a general category, now we're starting to talk about a bigger chunk of our income, right? But there's not a lot of substitutes for food as a general category, right? You know, it's like you can't, I mean, you can kind of substitute protein powder, I guess, right? It's not really considered food, but there's not a lot of things that you can do to substitute for food, right? So how does elasticity, so we just saw graphically how elasticity kind of dovetailed with the demand curve, right? In terms of there's different elasticities on the demand curve, and those correspond to different amounts of total revenue. Oh, sorry, that was up here. So the different elasticities on the demand curve, and they're corresponding to different amounts of revenue. So now we're going to introduce a new curve to the mix. And again, we're going to keep with this same demand curve that starts at 40 and ends at 80. So I'm probably just going to go over to the side here. Because again, we're just keeping that same demand curve. Oop. I can draw straight lines. I really want to take like a class in like how to do those like RS animate like sketches and stuff. I would love to be able to just like quickly like doodle stuff. Like I feel like it'd be a lot more entertaining overall. Anyways, I digress. So let's do 20 or 10, 20, 30, 40. And then it's got a slope of this 0.5. Again, I can draw a straight line. this is 80 down here. So this is our demand curve, right? And we know the equation for this. It's given to us P equals 40 minus 0.5 Q. And we did our calculus so that we figure out what the other version of this is, right? Which is Q equals 80 minus 2P. So right now we're going to graph a new curve, which is always, so if the demand curve goes through 80, then that means that my marginal revenue curve, so the amount of money, that I am getting for each additional sale is going to go through 40, so it's always going to go through half of whatever the x-intercept is for the demand curve. And it's always going to have a slope of twice the amount of that original demand curve. So our original demand curve had a slope of negative 0.5. This is going to have a slope of negative 1. Right? And remember, slope is rise over run. So this is what's called our marginal revenue curve. And our marginal revenue curve is telling us how much total revenue increases when the quantity increases by 1. So this marginal revenue curve, in truth, goes past 0 into the negative ranges, right? But we don't really care about that. Because when are we going to increase our quantity if our marginal revenue is negative? We're never going to do that, right? Never, ever, ever. So if this 40 quantity is ringing a bell for you, well, it should, because the 40 quantity is the same quantity where the total revenue is maximized. So where the marginal revenue equals 0, we have a Q star, where Q star represents the maximum total revenue. It's the Q star that's associated with maximizing the total revenue. So it's important to make that differentiation right now because eventually we're going to be talking about profit, not revenue. And so we're also going to use Q star as well for then, right? But it works in both cases. So when the marginal revenue equals 0, that's the maximum of our total revenue. It's how all of these things come together. Now we're out of time today. I'm going to leave off with just writing down the formula, and then we're going to start class on Friday talking about this. So our marginal revenue is related to our elasticity through this weird formula that luckily we are not going to have to know how to derive or understand why it is the way it is. We just need to know how to use it, okay? So we're not going to get all caught up in why it is this way. We're just going to do exercises in using it. So this is the link between elasticity and marginal revenue. So the elasticity is obviously the E's here. Marginal revenue is obviously the MR. Price is obviously P. All right, that's all for today. I will go ahead and I will throw this up on YouTube in addition to the other videos. Please come into office hours, send me some questions, do some math review. I'll also send out some Khan Academy links and some Khan Academy review for doing some algebraic solutions for two unknowns and 2 variables. So just please get familiar with that within the next week. We'll be showing up on the midterm, and I don't want it to slow you down. So have a great day.